Okay, so it's 4:30. After we finish the previous exercise, we will go over a new one, which is still a continuation of constraint optimization using the method of Lagrange multipliers. So, of course, as you remember, the posing of the problem is to find the maximum when you have a constraint, which is a restriction in the values. And the particular example is related to optimal allocation of resources. And the statement of the problem goes like this. So you have $600,000 to spend on production. And then, if X units of capital and Y units of labor are allocated, then you're given the information of the production function in terms of these two variables. Then you will have P units of production, so this will be produced, where P as a function of X and Y is of the form 120 times X to the 4/5 times Y to the 1/5. Again, the production function is given by a Cobb-Douglas model. So the characteristic of this model, as you remember, is basically the sum of the powers is 1, which is happening here. Some other information that you have is that each unit of labor costs $3,000, and each unit of capital costs $5,000. So the question is, how many units, X and Y, should be allocated to maximize production? So, before we go over the solution, just try to think a little bit about the problem, right? So this is the constraint. We have to formulate basically the spend, how much we spend, and it will be at most this value. In fact, we will make it equal to that value. Then under that constraint, we'll have this function, which is to be optimized, satisfying this constraint. Okay? So this is how much each unit of labor costs, this is how much each unit of capital costs, and these are the units of capital and the units of labor. Actually, yeah, there is probably a typo in the book, because actually what we will have is a constraint function of the form 3000x plus 5000y. But this should be accompanied by x and y. So since x is related to the capital and y is for the units, so it should be capital, it should be labor. Sorry about the typo. And so this is because the cost of capital is 3000x, and the cost of labor is 5000y. So just multiplying basically the price per unit for the number of units, and then the total cost is the addition of these two. And this could be named basically the cost of resources, when you add the cost of capital and labor. Now, since we have the constraint formulated mathematically, we can state the goal. The goal mathematically is to maximize the production which were given by the function p of xy, 120, x to the 4/5, y to the 1/5, subject to a cost constraint, which we already know. It's basically the function g of xy equal to 600,000. Right? So this is basically the total budget that we can spend. We expect that as long as we spend more, we will get better results. So this is the maximal thing we can afford. And this is basically indicating the cost, both for labor and capital. So in terms of the math, the problem is formulated now. Function to be optimized, constraint, and we know what to do. Find Lagrange's equations, solve the system of equations for the point coordinates x and y, maybe the coefficient lambda, which has a name, which is the Lagrange multiplier. But in any case, step by step, first thing is to write Lagrange equations. So if you remember, the first equation would be px equal to lambda gx. The second would be py lambda gy. And then you have a third equation, which is basically the constraint, which would be, in this case, 3,000 x plus 5,000 y equal to 600,000. So let's put a comma. If I take the derivative of this, well, this is with respect to x. I have 120, and then 4/5, x to minus 1/5, y to the 1/5. Then lambda gx, if I look at this function, is lambda 3,000. Also lambda gy is also easy, so it's 5,000. And then if I compute partial derivative of p with respect to y, well, again, right, x is constant, y is the variable, so I have the coefficient multiplied by 1/5, x is untouched, and then y 1/5 minus 1 equal to minus 4/5. So actually, you can put this in a nice shape. I could do, look, there are many ways of solving the problem. In fact, if you see in the different problems, everybody has their own technique, and I might not do always the technique of the book, but as long as the algebra is correct, your technique, the book's technique, or my technique is okay. So I can put this in the form basically y over x to the 1/5. This would be 120 by 1/5, and then I have x over y to the 4/5, just by putting this in a nice shape. And then that could basically indicate that lambda is equal, on one hand, to 120 divided by 3,000 times 4/5, then y over x 1/5, then this would be equal to 120 divided by 5,000 times 1/5, x over y 4/5. So I'm basically using by these equations, I will get rid of lambda. Due to the nice property that the powers, when they are added, they give you 1, I can pass to the other side and get basically this factor to the unitary power. And, well, yeah, I could also play with some algebra. I could basically pass some things to one side and some to the other. For example, I could do something like 5,000 divided by 3,000. Then the 120 factor comes out. This one too. Then this multiplied by 4, essentially. And then you have x over y, because when you pass to the other side, it's done, right? So the thousands also cancel. So this would be 20 over 3. So 5 times 4, 20 divided by 3. And then, let's see what else. Well, okay. So now we have the relation between x and y, right? We also have this constraint, which is what we intend to use. For example, well, from this, what you know is that x is equal to 20 over 3 times y. I can plug this back in, so 600,000 equal to 3,000. And I could actually, look, if you want, I could even do a factorization beforehand, which is basically 3x plus 5y equal to 600, right? Divided by the 1,000, and I'm okay. So then what I could do is to introduce this thing that I found. So I have, well, 3x equal to 20y, so 20y plus 5y, 600. So which means that y is equal to 600 divided by 25. And if you do the computation, this would be 24. That would mean that the x is equal to 20 divided by 3 times 24. So this would be 8 times 160. And yeah, okay. So at this point, the problem is solved. That would mean that the point x comma y would be equal to 160 comma 24. Again, everybody has their own method to solve equations. That is, of course, the way everybody thinks. So if you have a correct procedure, I don't mind, as long as it is logically correct. And then, well, basically what you have to do is to evaluate the productivity function at this point, right? So this is 160, 24, evaluating p. So if you remember, the function is 120. Then you have 160 to the 4/5. Then you have 24 to 1/5. You probably can do some factorization over here. Well, I mean, you can also put in the calculator, and the answer that you would get would be around 13,138 units. And yeah, but I mean, in terms of the procedure, it's kind of like, again, the good thing is that there is actually a procedure. I mean, except for perhaps the algebra that can get complex if the system of equations is not linear, and then you're at the mercy of all the algebra that you know. The methodology is pretty well indicated. Identify the constraint, identify the function to be maximized. We know that p is to be maximized. We have formulated the constraint as g is linear function equal to 600,000. Then, by knowing the Lagrange equations, which are px equal lambda gx, py lambda dy, equation of constraint. If I compute these partial derivatives, which is what I have done, this was easy because of the linear function. This I just have to do it step by step. Then, basically, well, I might, some possible way of doing it efficiently is to eliminate the lambda from these two equations. I played a little bit with the algebra. So I got this relation between x and y from these two equations by eliminating lambda. Plugging that back in the constraint, trying to make my life easier as well. Then I got the number for y, and from this I got the number for x, and I know the point. And then, of course, I know this constraint maximum, which is a maximum under a constraint. But, okay, is the procedure clear for everybody, what we have to do at each step? Yeah? Is there a question? Is there something unclear? Okay. So if the unclear part is the algebra, I would recommend you to practice as much as you can. There is no way around it. Okay? As you can see, there are many exercises, either in the book or in your assignments. So the way you develop like a little bit of a hunter's instinct for this is to do as many exercises as you can. So that's my only suggestion. Well, so we have done several exercises, last class and this class. But, well, there are basically two things to mention in this class. The first one is to give a little bit of an interpretation of what is the Lagrange multiplier. And the second is to give a geometric argument of why this method works. So, for the first one, in a way, you might have to believe me. In the second one, there is actually a very nice geometric argument. But what you could say for the moment is that before, say, the previous class and this class, I knew how to solve optimization problems to find a maximum and a minimum by the usual procedure where there was no constraint, which is, okay, find the critical points, etc., etc. In this case, what I did, in order to incorporate the constraint, is to define a new function, which is the original function, plus or minus a lambda, the constraint, such that when the constraint happens, which should be equal to 0, there won't be any difference with the original function. I got a new equation. You actually got 3 new equations, which were Lagrange's equations. And from that, basically I mimicked the procedure of the previous optimization into this one. So I kind of like gave some new equations, and you could see, okay, it kind of makes sense if I know that the constraint happens, but perhaps you're not completely clear on why the method works. you can identify some pieces in the puzzle, essentially, which is that the constraint is happening in the Lagrange equation, that because it happened, it vanishes. The function is to be optimized, but I'm sure that there is not 100% clearness on this topic, because it's the first time that you see it. So I will try to give some intuition. First, some significance that you will have to believe me. So regarding the significance of the Lagrange multiplier. So you could say that lambda has a useful interpretation. And it's basically a rate. So the statement goes like this. Suppose m is the maximum or minimum, depending on the kind of problem that you have to solve, value of the function of two variables subject to the constraint g of xy equal to k. So this is what you want to maximize subject to this constraint. So the Lagrange multiplier, which is lambda, is the rate of change of this maximum m. It's the same letter, although I wrote it differently, with respect to k. So what you have is lambda is how the maximum changes as you change the constant in the constraint. Think about the previous problem, right? Essentially we had the cost that we could use and we had an allocated budget. That k would be 600,000 in the previous problem. Now let's say that I get new sponsorship and somebody gives me more money, right? So that value of the constant can change. I'm changing the equation, at least in the value, which of course is going to change the solution of the problem in terms of the maximum or the minimum or the point where it is attained. So that is basically an interpretation of the lambda. And if you want to state it verbally, is a change in this constant m resulting from a 1 unit increase in k. So, anyways, we're going to use this concept in the next problem, where we'll use Lagrange multiplier as a rate, and the problem is somehow applied, and it's the following. It's actually related to the previous problem. So the manufacturer in the previous problem is given an extra 1,000 to spend in capital and labor for the production of the commodity in the exercise 7.5.4 that we have just solved. And if you think about it, basically you have a total of 601,000. And now what you have to do is to estimate the effect on the maximum production level. So, well, I'm not going to state the previous problem again. We have just seen it, literally. And, well, we identified that basically in that case, well, before, essentially, what you had is that the production at the maximum point that we found was around this value. So, okay, yeah, this is all what I have found before. What I could do is to compute lambda. If you have noticed in the previous problems, I always get rid of lambda in order to get an equation between x and y, to plug it in the constraint. So now let me compute. If I use one of the formulas, actually, if you want, I could show you where we got this relation. But, well. Let me see. Well, look, essentially, if you play a little bit with the algebra of this equation, yeah, by making the division of 120 by 5, you would get this other equation that I'm presenting to you, so just keep it in mind. To the same power 4 over 5, let's say I plug in that value. So 24 over 5,000, now evaluated at this point, where x was 160, y was 24, and then to the 4 over 5 power. If I do the computation in the calculator, this is 0.0219. So, this lambda is a unit rate of change. So this is, again, in this way to approximate the delta increases as a derivative. If I change k by 1, that would be the change presented in m, by definition. So, the maximum production with the new cost constraint would increase by, let's say, approximately 0.0219 units. This is an approximate result for each dollar that you increase in the constraint. Now, the increase was not for $1, it was for this 1,000. So, in that case, the maximum in the production increases by, well, just multiply 1,000 lambda, which is, well, you have to basically just plug in the value, 1,000, and then 0.0219, so 21.9, so just change the decimal 3 units, and then that would change the maximum to, I would just have to add this, well, 131.9. So this is the previous maximum that we had. This is the addition, right? I mean, again, I'm using this basically, okay, if I know that lambda is the m over dk, is approximately delta m over delta k, where now this is not a limit, but this is actually an increase, okay? I mean, if delta k is 1, that's how you see it, that you will have a change of delta m, right? Approximately. That's why you call it basically this unit increase. So I'm doing basically this change in the maximum, which is what I computed here, and then I just added to get the new one. Of course, you can verify that this actually happens. The other way to do it is essentially to solve problem for the constraint equal to 601,000. If you do the procedure, you will get around the same value. Not exactly the same, because there is an approximation. This is an equality. This is approximate. But you will get around the same values. And at the end of the day, computing, both in your job or for a computer, costs time. So as long as you can provide a method of approximation that gives you the answers faster and that is reliable, that is good for you. Okay? So, of course, you could repeat the problem. That is perfectly fine. Let's say that for some reason you have to do 1,000 of these problems by just evaluating different scenarios. Well, instead of doing the problem once, maybe this would be easier to compute. In any case, that would be for you to verify. And there is just one definition or some notation into some of these quantities, which is basically a mental note for you, that the type of problem of example 7.5.4 is called fixed budget problem. And in that case, lambda is called the marginal productivity of money. Again, the marginal is always related to a unit increase, so it kind of makes sense by definition of the lambda over here. In the previous example, 7.5.3, lambda is sometimes called the marginal utility of money. Okay, so that's just a mental note for you. And after that, we have two more parts, which is to solve a function of three variables with a constraint, and then the geometrical significance. So the new part, okay, Lagrange multipliers for functions of three variables. The method is going to be the same. Just bear in mind that you will have one more equation, which is probably going to be of the form fx equal to, or fc equal to lambda g of c. But now you will have basically four variables, right? Because you will have x, e, y, and lambda. Usually you do not care too much about the lambda, that's true. But still, in terms of the dimension of the problem, you will have a system of four equations in four variables. So the problem now is to optimize a function of three variables, x, y, and z, subject to the constraint g of x, y, z equal to k. So now what you have to do is to solve the set of equations fx equal lambda gx, fy equal lambda gy, fz equal lambda gz, and g equal to k. So again, four equations, four variables, x, y, z, lambda. Okay? It might not seem that complicated. It takes time. Okay? So especially when the system of equations is not linear. If it was linear, okay, maybe you can do Gaussian elimination, that stuff. If it's not, it depends on which kind of functions you have, and then you have to refresh your algebra. So the problem, to see how this is done, is 7.5.6, which is related to minimizing the construction cost of a box. So the box is kind of made of different materials regarding if it's like the top or the bottom, etc. So the material costs $1 per square inch for the bottom part, then $2 per square inch for the sides, and $5 per square inch for the top. Now, here comes the constraint, of course, right? So if the total volume should be 96 square inch, which dimensions will minimize the total cost? And then the second question is, what's the minimal cost of construction? So, well, part of the problem is identifying what is the function to be optimized, also the constraint. At the beginning, it sounds like the typical problems of maxima and minima that you have done maybe since high school, in a high school calculus course. There is a difference with the constraint, so you should keep that in mind. So let's make a picture in order to make things a little bit more clear. I will draw my box. And so x, which is the depth, y is the length, and z is the width, where of course these numbers are positive. This might come in handy later. And the volume of the box is simply the product x, y, z. Okay, so far so good. Now, if you think of the statement of the problem, the volume is the constraint, because you know that the product of these three numbers should be 96. So just keep it in mind. Then, how to formulate x, y, z? I'm sorry, I know that in Canada it's common to use the z. For me, I did a PhD in the US, so the C is imprinted with me. So sorry if I bring you to confusion, but I try to as often as I can to say the Z. If you hear C, is most probably because of the Z, but unless there is an actual letter C. So the total cost of construction will be basically the sum of the parts, right, multiplied by the price. So we'll write the parts. If you look at YZ, that's basically related to the bottom. So one stands for the price, and then this is per square inch. So by the product, you determine the number of square inches that you have. Then let me write this factor, and I will explain why. So in this case, you have the price for the sides, and then you have two of these sides and two of these sides. One of them is xy, the other is xz. X is this depth, right? So you have this, and then twice. Then you will have 5yz, so 5 is for the cost, and then yz, sorry again, that is because the material has a different cost regarding being either the top or the bottom part of the box. So just to make it clear, this is the bottom part. These are basically the four sides. Two of them are of the same dimensions, have basically two pairs. And then this would be for the top, where you have each allocated cost. Well, this one will be the same, so you have 6yc, I adding these two. Then you have plus 4xy plus 4xz, just by doing this multiplication. So, now, well, in this type of problems, you want to minimize the cost, right? So this is the function c that you want to optimize, and this is the constraint. And if I even write basically b equal to 96, this would be the function b of xy, that is the constraint. So mathematically, now we formulate this problem of three variables plus the Lagrange multiplier as to minimize the function c subject to the constraint b equal to 96. And so what you'll get is, of course, now four Lagrange's equations, the same way we wrote them before. So you have cx equal to lambda bx. So this is the function to be optimized. This is the constraint. cy lambda by, cz equal lambda bz. And then you have b equal to 96. Three equations plus constraint. Four variables, x, y, z, lambda. So you get three new equations. Now I basically have to keep track of where this is. So if I take, so you have 4y plus 4z equal to lambda, then yz. Remember that b is equal, can you see? Yeah, xyz. Then you have this function, just remember it. So cy, 6z plus 4x equal to lambda xz. Then partial derivative of this with respect to z, 6y plus 4x equal to lambda xy. I mean, the product is nice enough so that you just make it disappear and you have the function. And then the constraint is xyz equal to 96. So far so good, right? At least in the way we have to do this, right? 4 equations, partial derivatives everywhere, constraint. Well, so again, in this case, basically you might have your own way of thinking. I'm not going to dispute that, and so I'm going to present one way of solving the problem. It's not the only way. Possibly the book makes it different, but I'm just trying to make my life easier. That is my motto, which is that if I essentially see that the product of these three is 96, what I could do is to multiply back again this by x, this by y, and this by c, and I just plug in the 96. So that might be easy, right? So what if I do something like multiply by x, by y, and by c? On one hand, I would have lambda 96, and then I have 4xy plus 4xz. Then I have lambda 96 if I multiply by y, 6yz plus 4xy. Then I have lambda 96, 6yz plus 4xz. So far so good. Everybody with me? I'm just using the constraint. Yeah? Is there any question? Okay. So I could try to do the same kind of things that I was doing before, which is essentially try to get rid of the lambda. Actually, if I notice, well, I could get rid of this xy because it appears in this equation and in this equation. So if I take, for example, this equation minus this equation, this will disappear, I will have the other, right? So if I use these two, essentially, this minus this, I have 6yz minus 4xz equal to 0, right? So, well, that I could actually factorize, for example, as the form z times 6y minus 4x equal to 0. And I know that, of course, I mean, x, y, and z cannot be 0. So the only way that I could have this is essentially if 6y is equal to 4x. So at least I have a relation for that. So far, so good. Moreover, yeah. Well, I could basically, want to use again one of these equations in order to, I will use this relation actually. Because 6yz equal to 4xz, both of these two appear here. So if I plug in this one, what this is telling me is that 6yz is equal to 4xz. So I have this. I can basically substitute this one with this one. So what I would have is lambda 96 equal to 12yz. I just use this. I put instead of 4xz, 6yz, 6 plus 6, 12, and I have this. And so, in fact, if I do a multiplication of x and x, I have that this is again 96. So what I would have is that x lambda 96, well, actually I get rid of the 96, and I have 12. So that would mean that x is equal to 12 over lambda. I'm trying to take the path of minimal resistance on the way I solve the equations, because I want to make my life easier, not more complicated. So maybe that's why there is a choice. I'm basically on the process trying to eliminate as many variables as I can. I have a relation between y and x, I have a relation between x and lambda. I can plug in back this, and I can use also one of the equations that I had before, which is, for example, wait a second. So, yeah. X y plus 4x. Yeah, okay. Well, essentially, from these conditions, you can derive an equation of this form. Actually, you can derive two equations of this form, which is 6z plus 4x equal to 12z, 6y plus 4x equal to 12y. From this, you could derive 6z equal to 4x and 6y equal to 4x. From these two, basically what you will get from this equality is that z is equal to y. And given the relation that is happening over here, for example, what you would have is that x is equal to 3z over 2. I will pass the notes in clean if there is any confusion. And then, if I plug in these relations, z equal to y, x equal to this, I know that 96 is equal to x, y, z. So what I would have if I put everything in terms of z is basically 3 halves, plug in the z, c cubed. So if I do the simplification, basically I have that c cubed is equal to 64. And that would mean if I take basically the cubic root of 64, basically you have 4. So that would mean that y is also equal to 4, and then x is equal to 3 divided by 2 times 4, so 6. So you would have x, y, z equal to 6, 4, 4. You could solve also for the lambda. So keep in mind that, of course, in the process, what you have to do, because at the end of the day you care about x, y, and z, perhaps try to get rid of the lambda as soon as possible. Try to play, for example, with the product. Once you get the relations, hopefully you got the relations between x, y, and z. And if I evaluate, basically, now that I have found this point that satisfies the Lagrange's equations, what I would have is that the constraint minimal cost is just the evaluation of the function, right? So if you remember the cost function, you have this. And you will see actually that there is some symmetry happening. Because let me write, when I plug in y and z are equal to 4, and x is equal to 6. So you will see in the coefficient how this minimization is kind of happening. So you have 6, then y and z are equal to 4, so this is 4 squared. Then you have 4 times x, which is 6, and then times y, which is 4, and then you have 4 times x, which is 6, times which is 4. So you have 3 times this product, okay? So you have basically 3 times 6 times 4 squared. So, I mean, I don't want to be a numerologist, but if you think about it, this is basically looking for the values of x and y where you have this symmetry. You know, you always have the 6 and the 2 fourths. You see? You had different coefficients, but it looked for the minimum where you basically y and z had the same value, and the x had the 6. And I don't think it's no coincidence that you have actually 3 times this summand. It is because it's looking for a symmetric solution in a way. So if you do the computation of 3 times 6 times 16 is 288. There is a typo in the book actually because it says 228, I think. Just keep it in mind. And, well, loosely speaking, this would be the way you would solve the problem. But as you can see, the complexity of the problem increases when you add one more variable. Because, okay, 2 equations for 2 variables is like intersecting a line, unless you have a very crazy function. 3 equations in 3 variables, it depends on the function, but if you play around, you can get by easily. 4 equations, it's going to take some time. And if the function is not linear, you basically have to be careful on how to play with the function. So just keep it in mind, dimension takes a role in here. And the last part is basically to explain why the method works. So why does the method of Lagrange multipliers work? And perhaps a picture could explain it very intuitively. Let's say that I have a constraint curve, right? And then I have a function to be optimized. Of course, the function can take many values, but I want to look for the point that, say, minimizes or maximizes that function. Let's say maximize in this case, but that it satisfies the constraint. If it satisfies the constraint, it must be along this line. Now, what I can do is to study the level curves of the function to be optimized. This is the constraint. So if you want, I can make a clarification. This is basically the constraint curve of the form g of xy equal to k. And then I would have families of functions, right? Let's say something like this. So let's say that the value, basically these are level curves of the form f of xy. This is the x-axis, this is the y-axis, equal to c. And what I'm doing is to draw the level curves. They are curves, right? I increase the value of c in this direction, for example. And I look for the one that maximizes this f, but that it still satisfies the constraint, meaning that at least it has a point over there, which would be basically this, that only has a single point. And so what will happen is that essentially the level curve, which is happening here, and it's having a single point of tangency, is precisely tangent to the constraint curve. So this would be a direction in which the value of c increases. This is the constraint curve. These are basically level sets, if you want, or level curves. This is a so-called point of tangency. Let's say, for example, we have a value c that is higher, but it doesn't satisfy the constraint. So this is a so-called point of tangency. And this one, the one that is basically touching, like just kissing the constraint curve, is the highest level curve, meaning the highest in the value, that intersects the constraint. So you see, I mean, if I want to maximize, look, without the curve, maybe I would have to find the critical points, etc. But the constraint makes a difference because I have to be in this curve. So this is basically, I'm trying to find the one that gives the maximum value of f by going over the level curves, and the one that gives me the maximum value, but that still has at least a point in the constraint, is the one that is kissing. So the geometric argument is that for any function f of x and y, the level curve, let's say f of xy equals c, has a slope at each point x comma y given by dy over dx equal to minus fx divided by fy. So look, there's a reason we're studying level sets or level curves, because both this formulation and this formulation are using a level curve. And if you want to see where this is coming from, it's basically because in a level curve, because the value is constant, what you have is that the change in f is 0, which means that you have fx dx plus fy dy. This is like a differential formulation of the level set. Because if you're in that curve, the value of f, capital F, doesn't change. If you play with the algebra, you get this relation. This is giving you the slope. And so what we will do in the next class is equate the slopes obtained from the constraint curve, which is a level curve for G, with the slope of the other curve, which is a level curve for F. But this is where it's coming from. So we will do an equality of these two slopes. So I have set up the geometric idea. We will continue on next class.